Hello, everyone. I'm Landon Breeding. I'm excited to present a case study on how we incorporated GIS and hyperspectral data for gold mine exploration at Frisco Gold Mine. The main objective of this, sorry. Okay. Okay. The main objective of this project was to conduct a data compilation of historical and contemporary data related to Frisco Mine and explore the potential benefits of integrating digitized geologic maps and hyperspectral data for identifying new exploration targets. We aim to leverage advanced GIS tools and techniques to streamline the target identification process and gain a better understanding of the geologic processes in the study area. The mining industry has been evolving rapidly, and the efficient utilization of advanced technologies is becoming increasingly crucial. Incorporating GIS and hyperspectral data in exploration projects can assist in how we approach gold mining operations. By digitizing valuable geologic information from traditional paper and analog maps and integrating it with hyperspectral data, we can enhance the accuracy and precision of exploration efforts. This integrated approach enables us to identify potential gold mineralization zones more effectively, leading to optimized resource estimation and improved targeting in gold mining operations. The Frisco Gold Mine is located in the San Francisco Mining District, situated within the Black Mountains of Mojave County. The mine is approximately 25 miles west of Kingman, a city with a population of around 28,000, and about 9 miles east of Bullhead City, a city located along Colorado River. Additionally, Las Vegas, Nevada is approximately 90 miles south of the Frisco Mine. The geographic location of the Frisco Mine in Mojave County places it in an area with a rich mining history. Mojave County has been known for its mineral resources and has seen mining activity for several decades. The Frisco Gold Mine, dating back to 1890s, has experienced intermittent periods of production and exploration over the years. The geological composition of the area is primarily made up of volcanic tuff, gneiss, and granite. Tuff is a type of volcanic rock formed from consolidated volcanic ash and fragments. It is often porous and may contain mineral deposits of economic interest, such as gold. This layer overlays gneiss, which is a metamorphic rock that was once either an igneous or sedimentary rock. It typically exhibits banding, texture, and may contain mineral alterations indicative of potential mineralization. The last rock type that is part of the geologic makeup of Frisco Gold Mine is granite, an intrusive igneous rock that is coarse-grained texture. While granite itself may not host significant gold deposits, it can be associated with hydrothermal processes that lead to formation of gold-bearing minerals in the surrounding rocks. The Black Mountains Detachment Fault is the boundary that separates these distinct geologic formations. This map is a reference map of the Frisco Mine. It shows the main cities near it, as well as the major and secondary roads. The Frisco property dates back to the 1890s. Gold production at the Frisco Mine has been intermittent since its discovery in 1890. Approximately 36,300 million tons of ore at 1.37 to 2.06 grams a million tons of gold were produced from the underground workings between 1890 and 1930. Production stopped until the 1970s when multiple companies, including Red Dog Mining, Frisco Landon Mining, and Gerald Gold explored the property and completed compliant resource estimates. Upon its acquisition of the property in 2011, Frisco Gold Corporation contracted Geographics Consulting LLC to gather additional historical and present-day data in order to evaluate potential exploration targets. To achieve this, advanced GIS tools and techniques were used to conduct a comprehensive data compilation and to further investigate the Frisco Mine. Why data compilation is important? Well, it gives informed decision-making by building a comprehensive geologic database compiled through integration of various data sources. It empowers exploration and mining teams with a wealth of information. Having access to a wide range of historical and contemporary data, including geologic maps, hyperspectral imagery, and production records, enables geologists and mining professionals to make well-informed decisions at every stage of the mining process. Target identification. Through the compilation and analysis of comprehensive data, potential exploration targets can be identified with greater accuracy. The integration of digitized geologic maps, which provide valuable insights into the distribution of rock types and geologic structures with with hyperspectral data that reveals alteration zones, facilitates the precise delineation of areas with higher likelihood of gold mineralization. Understanding geologic processes. The combination of historical and contemporary data allows for a deeper understanding of the geologic processes that have shaped the Frisco gold mine. Analyzing changes in geologic features and identifying trends in alteration patterns contributes to a more comprehensive geological model, enhancing the predictability of mineralization occurrences. The historical data added to the compilation included geologic Frisco maps from 1987. This geologic map was produced at a scale of 1 to 1200. The legend includes the geologic dates for the lithologies as well as the geologic structures present in this geologic map. This map specifically highlights the geology of two potential explorations on the Frisco property, namely Gold Dome and Gold Crown. This figure serves as a visual representation of the lithologies present in the area and the geologic structures that were identified during the mapping process. If you look close enough, there are lighter and darker colors used for the same lithology. This is due to the different approach taken by the geologists at the time of mapping the Frisco property. Ed Hutchinson assigned a darker color to the areas that were visible at the Frisco site when assigning the same base color, only lighter, to the same lithology that was presumed to be present. This approach provides a more accurate representation of the geologic structures present. This is another geologic map of a different section of Frisco mine, which shows the granite extension and south area of the Frisco property that is being viewed for further exploration, called section 16, which is south to the geologic map above. This geologic map again shows the lithologies of the area and geologic structures present. The contemporary data added to the compilation included this map from the Arizona Geologic Survey. The preliminary geologic map of the Union Pass Quadrangle, Mojave County, Arizona, is a geologic map that shows the regional geology. This map has a scale of 1 to 24,000. The projection that is used is UTM NAD 83, Zone 11. Small-scale geologic maps offer a regional perspective, allowing for a comprehensive understanding of the geology over a larger area. They provide an overview of the major geologic features, rock formations, and structural trends within the mapped region. The other maps that were used in the compilation included geologic maps of the surrounding Frisco area, downloaded from Gold 79. The Sheep Trail area map with a scale of 1 to 200 and the projection of UTM NAD 83 Zone 11 North has 4 main geologic lithologies present that include alluvium, Miocene rhyolite, Miocene andesite, Precambrian granite, and geologic structures like faults and veining. The Tyrone mine is another area that was important for the understanding of Frisco mine. The Tyrone mine is just north in relation to the Sheep Trail mine. And the last area of importance of the Frisco mine was the Gold Chain region. The Gold Chain is located directly to the west of the Sheep Trail mine. Here's an image on how these 3 areas are in relation to one another, Gold Chain being on the left, with the Sheep Trail just next to it on the right, and Tyrone mine being directly above that. These geological maps offer a pivotal point of reference for understanding the Frisco mine. By examining and digitizing the mineralization patterns, rock formations, and structural features present, we can draw parallels to potential geological characteristics in the Frisco mine region. These maps allow us to identify shared geological elements that might signify similar mineralization processes guiding our exploration efforts. The last piece of information that was deemed important in the data compilation of Frisco mine was the hyperspectral map that shows the different alterations of the Frisco mine. The teal and red borders represent section 16 and Frisco patented claims, respectively. The light yellow represents phyllic alterations. The red represents argillic alterations. The purple represents the hydrosilica alterations. Green represents epidochlorite alterations, and the blue represents the carbonate alterations. This map was downloaded from the USGS website and tells us a lot about potential mining explorations. Understanding the characteristics of phyllic alteration is crucial, as it involves the replacement of original rock minerals with sericite, quartz, and pyrite through hydrothermal activity. Typically, this alteration is found in the upper levels of epithermal gold systems. These minerals suggest the presence of hydrothermal fluids enriched in gold and other associated minerals, making phyllic zones a potential target for gold exploration. Argillic alteration, on the other hand, involves the introduction of clay minerals and is commonly associated with the upper parts of epithermal deposits. This alteration is identifiable by its white to grayish alteration halo and can serve as an indicator of the proximity of gold mineralization. Understanding both types of alteration can help identify potential gold mineralization areas. The argillic and phyllic units were mapped at 30-meter spatial resolution, and the hydrothermal silica-rich rocks and prophylitic units were mapped at 90-meter spatial resolution. The methodology for digitizing the geologic maps follow this workflow. To import the data into Discover, the PNG file of the geologic maps were added to the Discover interface. DataMine Discover is an all-inclusive software tailored for geologists and exploration teams in the mining industry. It provides numerous tools and capabilities for geologic data management, analysis, and visualization. DataMine was the most efficient software to use given the parameters of this application. The next step after this image was imported into Discover was to georeference the analog data with the spatial coordinates and assign the best fit coordinate system for the Frisco mine study area. The coordinate system that was used was UTM NAD83 Northern Hemisphere Zone 11. The coordinate system was used because it offered the least amount of distortion for distance and direction for the Frisco mine area. The next step of the process was to begin tracing lithology contact lines and any geologic structures that were apparent, such as faults and veins. Other line digitizing tools that were used in this process were snapping to guarantee precise alignment and connectivity of line segments. Editing and modification tools were also used to adjust the position of vertices, reshape lines, delete or add vertices, and perform other editing operations on the digitized lines. Once the lithology contacts and faults are digitized, the topology check tool was used to highlight any errors that may have occurred, such as overlapping or crossing lines that should not intersect. This tool is specifically designed to validate and verify the connectivity and integrity of line features within a data set. The next step in the digitizing process was to create polygon features from the digitized lines. These polygon features were labeled with the corresponding lithology code. A color picker was then used to extract the RGB that the specific lithology was given on the analog maps to match the digitized lithology polygons to keep clarity and transparency from the analog maps to the digitized maps. The Frisco geology maps from 1988 had two colors representing the same lithology, with the only difference being whether the lithology was seen mapped or it was presumed. Those differentiations were taken into account in the digitization process as well. Once the polygons were attributed and color-coded, the next step of the process was to begin attributing the different kinds of contact lines that were present. Lithology contacts, such as contact approximate, were assigned when the contact line was a dashed line on the analog map. Contact accurate was an attribute that was assigned to the lines that were solid on the analog map. And lastly, the contact concealed was a contact attribute that was assigned when the line was a thick dashed line. These attributes were taken from the Arizona Geologic Survey map of Arizona to ensure consistency throughout. The digitization process described above was repeated for both historical and contemporary geologic maps. This approach allowed for the comprehensive compilation and integration of data from different time periods, enabling a better understanding of the evolution of geologic features over time. The results of this case study were a comprehensive exploration of Frisco mine area was conducted with the assist of historical and contemporary geologic maps and hyperspectral data. Integration of hyperspectral data provided detailed insights into mineral composition for mineral exploration and sustainable resource management. Valuable geologic databases were created for future research and scientific inquiry. And integration of historical knowledge with modern technologies helped assist in informed decision-making. And that's the end of my presentation.